third and final phase is called data interpretation. In this phase, the geoscientists and the petroleum engineers must interpret the significance of the lines represented in the survey's charts and graphs. Do these lines form images that resemble geological structures? If so, what kinds of geological structures? By studying these surveys, the geoscientists and petroleum engineers must figure out where the domes might be, where the faults might be, where the oil might have accumulated in the subsurface. In the first two phases, the data acquisition phase allowed them to get the data, while the data processing phase allows them to organize, perform calculations, and compile the data. Now they must decide what all this compiled and calculated data means. Because much of their data is only representative, not a true snapshot, it is sometimes difficult to see what actually lies in the subsurface. Like a radiologist with X-rays, geoscientists must rely on their knowledge and experience to interpret what the data is representing. Let's look at some examples of data interpretation. They will help you make decisions about exactly where to drill a well. It is here that art unites with science. What do I mean by art uniting with science? Because none of our images are real, but are, in fact, compilations of computer-generated data graphed on a chart or manipulated into a three-dimensional image. The geoscientists must still give meaning. They practice the art of trying to imagine or see the structures as they actually are, understanding how oil is created as it actually was created. They must be able to envision what all of these lines, images, blank spaces mean. Next, it is also advisable to have someone with experience, someone who has practiced with reading the charts and then comparing these charts to the actual formations and structures identified and verified by actually drilling down into the subsurface. Here is a seismic survey that has been colored by the computer or the geoscientist using different colored inks. Look at this for a second. Can you spot the faults? Now look at it again with the yellow lines added. Now do you see them? Here the chart is without the yellow lines. Do you see the structures? And again with the yellow lines. Can you spot the fault? According to the way the lines are represented, we have a normal fault. We also have two horizons. A horizon is an area on the survey that has been identified to have interesting sedimentary rock. Horizons are usually colored red by the computer to make them easier to see. On this chart, we also have coordinates. Again, they make the charts easier to read. The x-coordinate is the distance, usually measured in feet or meters, and the y-coordinate is the measurement of TWTT. These two-way travel times are 1 second, 2 seconds, and so on. The two-way travel time, or TWTT, is the time that the sound wave takes to travel from the energy source after the wave has bounced off a boundary and then reflected back to a receiver. The computer has plotted the data, but it is humans, geoscientists and petroleum engineers, who must tell what it means and draw conclusions. Are these faults large enough to contain traps where oil and gas can accumulate in large enough quantities to be commercial? Geoscientists and petroleum engineers interpret the seismic data to understand the subsurface geology and to assess the likelihood of finding oil and gas accumulations. Geoscientists and petroleum engineers interpret the seismic data to understand the subsurface geology and to assess the likelihood of finding oil and gas accumulations. As I have repeatedly said, seismic surveys help us visualize what is in the subsurface. For structures like structural traps, they are excellent. Unfortunately, they are not so helpful in identifying formations like stratigraphic traps. In these instances, geologists and geoscientists must use less direct tools and methods to try to understand the subsurface and then interpret what is there. For instance, to help depict stratigraphic traps, geologists use a technique called projecting backwards in time. Simply put, this is a method where, looking back in time, they visualize the locations of the mountains, rivers, and oceans that were present when the reservoir rock was first deposited or laid down. From there, they piece together possible sequences of ancient events and figure out the odds or the likelihood of a trap having been formed. They try to reconstruct the sequence or order of geological events that happened millions of years ago. By understanding what might have happened first, then second, and so on, may give them an idea of whether a reservoir rock will be productive. They interpret, theorize, and then make models in their attempts to understand how the formations were formed in the subsurface over time. Let me illustrate. Here, an initial dry hole was drilled and only shale was found. No oil was found. You know that shale can be a source rock for petroleum, so you try to imagine where the petroleum that might have formed in the shale might have migrated to. Using your subsurface maps, you figure out where the ancient high is, for example, a shoreline or a mountain slope. Could oil, formed in the shale, have migrated toward the ancient high and got trapped? Is there sandstone or reservoir rock to which the oil could have migrated? Could the ancient high be made out of impermeable rock, and could it have operated as a trap? These are questions you ask before you decide where you will drill your next well. Another method is called following or extending trends. Let's look at this illustration. Let's say you have an existing field nearby and theorize that oil formation could run along a straight line. Could other petroleum traps be situated along this line further out? You follow that line hoping to discover other accumulations. You must keep in mind, however, that curved lines, as well as straight ones, can also join 2 points. By projecting out a straight or curved line into a new field, you might find that oil was trapped in a similar trap along this same axis. This is called interpolation. You may have to consider other, more convincing data to confirm your ideas. Using different techniques in data interpretation, we look for contrasts in contour lines of the wavelets on the page. If we look closely and have a trained eye, we can see the outline of a possible anticline or fault. This is why in seismic we do kilometers at a time. This allows us to view large areas, so when we put these charts together, we can see if these lines come back down to form an anticline or if they are just inclines. If you look where the middle red arrow is indicating, you can see the top dark line has terminated. Maybe this is a fault. Even without drilling a well, we now have a good indication of what is down below. But with all this information, remember that 3 out of 4 wildcat holes are still dry.